going on at the EGU2009, and we have invited a few experts to hold a talk on this subject. First is Caitlin Buck of the Department of Probability and Statistics, University of Sheffield. She will do an introduction on why we are here talking about uncertainty in the first place. Uncertainties, what do we know and how do we actually manage them? And she will also say something briefly on the challenge to actually quantify these uncertainties. Then we have Chris Forrest of the Department of Meteorology in the Penn State University. Chris will give a breakdown of what is known and unknown at this current time. He will give an overview of session CL52 and highlight some of the talks being held there. He will elaborate on what we actually know about the climate system and about their uncertainties, and about the use of climate models to make predictions and actually understanding the quality of these models. Now we have here Ron Prinn of the MIT. He will discuss the latest predictions of 21st century findings from recent MIT uncertainty studies. And Tim Carter will also present some slides, and he will be available to answer any questions you might have. Caitlin?
Thank you. So, some of you might have thought when you saw the press release for this press conference, why is there anybody here entirely interested in talking about uncertainty? And so we're going to try and explain to you why we're here, what motivates us, what makes it, why we think it's important to focus on uncertainty. And the core of this is that we believe very firmly that a single number estimate for an aspect of future climate is not actually very useful. It's not very useful because all of the pieces of information that are put together in the jigsaw that tell us about future climate are themselves uncertain. So the idea of seeking a single number that might summarize what will happen in the future seems very unhelpful and very unsensible given the current situation that we're in. So we have lots of uncertain information. We're going to combine it together, and then somehow out the other end we've been thinking that we should be trying to get a single best number prediction. So for example, a prediction of the temperature for July in Austria in 2100. Lots and lots of people have been trying to do that. Produce maps of the world for a particular time in the future with single number in each cell telling you what the temperature is. And it's the opinion of almost everybody speaking in CL50 and CL52 that we should stop trying to do that. It's unrealistic and it's not helpful. What we should be doing is we should be trying to provide a statement about the uncertainty, and that statement of our uncertainty should form a key part of all climate predictions. We need to find a way to quantify those uncertainties and to present them in very simple, intuitive and interpretable ways. And it's uncertainties both on the inputs and on the outputs that we need to quantify. But we can't do a good job at quantifying the uncertainties on the outputs, the predictions that we want to make, unless we quantify the uncertainties properly on the inputs. So we've been talking around all of these issues in CL50, and tomorrow they'll be doing the same kind of thing in CL52. The point is, the really key point here, is that if we don't keep track of uncertainties at every step of the way through the process, in particular if we focus on the most likely value at each step of the process, we're losing information, the fuzziness, if you like, that's in the edges of the information that we have. And if we do that repeatedly, step by step, as we go through our process of trying to understand what's going on, what we're doing is at each step of the way, we're losing the most extreme things that might happen. And if we do that repeatedly, the outputs that we've got can't possibly do a good job of assessing the extreme values, the most unlikely things. And those are the things that we really want to know about. We really want to know about high temperatures, high humidity, low rainfall. And if we can't be sure that we're doing a good job at capturing those probabilities, then we are going to be very, very unlikely to make good decisions for the future. So it's all those key issues that we're talking about. So just to focus for a moment on the very specific kinds of things we're doing. Suppose we want to predict the change in temperature in a particular place, or on average for the entire globe, between 1990 and 2100. What a lot of people have been trying to do, and what a lot of decision makers seem to be thinking that we should provide for them, is a spectrum with a pinpoint in it like this, where we say the most likely temperature change in that period is in the window 5 to 6 degrees. And what we're saying is that all of the information that feeds into this process is uncertain. And it's just not realistic. We can do it. We can give you a single best guess. But actually, that's what we really think. Right? We can give you a best guess because we can tell you it's in this bar. But that's not really very sensible because there's actually quite a lot of probability in this bar. And we can give you a number for how much probability there is in that bar. And we would really like policymakers and members of the public to begin to be thinking in these terms when they ask us about what's the probability of climate change. To think about climate uncertainty, climate change to be represented in terms of histograms or bar charts rather than single numbers. And everything that we're doing is trying to provide tools to do a better job to quantify uncertainty in these kinds of terms and to stop doing it with single number summaries. So that just to give you a mental picture of how we see the process of taking data and creating estimates of future climate, we see it, if you like, as a three-step process. We have inputs, and the inputs consist of 20th century, high-quality 20th century data, which nonetheless have some uncertainty associated with them, but typically uncertainty that we really understand quite well and that we can very easily draw those little pictures for. We can very easily draw the range of uncertainty as a picture. We also have lots and lots and lots of much less high-quality data that we call proxy data that comes from places like ice cores and lakes and all the other places that you'll have heard people talking about here. Now, the uncertainties on those are hugely variable, both in terms of their scale and their nature. And for those in particular, it really isn't sensible to be asking the scientists to give you a single number. You should be encouraging them to give you little pictures that show the general range of ideas, the full spectrum of possibilities, particularly because they're going to be used as inputs to this process. And if we encourage them to chop off the tails of the distributions and give us only the best, most likely value, then we're losing, right from the beginning, we're losing those high-risk things that we want to know about when we come out this other end. And if we do that on the inputs, we can't possibly see them in the outputs. Okay, so we're going to put these things into our big climate models that represent the physical system. And the guys working in CL52 are going to tell you quite a lot more about this process here, so I won't say very much about that now. But the point is that this modelling system is what allows us to put together all that data at that end and to make our outputs. And our outputs are in some sense future climate. Things like estimates of temperature and rainfall for 100 years from now. Okay? And those also, of course, should have distributional forms, those little graphs. Okay? So what we've been doing, CL50 actually happened yesterday. There were a lot of members of the group that spoke in CL50 around, and so they'd be very happy to talk to you. What we've been focusing mostly on is doing a better job at quantifying the uncertainties on the inputs to the climate models. And we work a lot with the proxy data, the very, if you like, the very dirty data that has very large uncertainties, all sorts of complex forms for the uncertainties, and some of us are working on building better tools for handling those uncertainties. And some people are working in the field to try and get more data to help us do a better job at quantifying the uncertainties. Unfortunately, those talks happened yesterday, but as I say, quite a lot of people are still around if you'd like to talk with them. CL52 will happen tomorrow, and there are several members of that group here, and they're working on improving the uncertainty estimates on the projections, on the outputs of the model. So is it easy to go back? Thank you very much. So they're working on these two bits, and they're going to talk to you now about what they're planning to do.
Okay, thank you, Caitlin, for a good introduction. we're working on. So we have a few minutes now here where I'll now talk a little bit about what we think we know about uncertainties, what we know for certain about the climate change problem, and give you a little bit of a preview of what we're going to be talking about tomorrow in our session CL52. So the first part is, what are the things that we know for certain? And we've divided it up in our session tomorrow essentially into the issues related to observations, what's related to the climate models themselves, and then what are the uncertainties in the predictions. And so regarding the observations, it's very clear we don't want to get into a situation of misrepresenting, for example, what was said in the IPCC or those sorts of issues. But it's very clear from the observations that the climate system is warmed over the past century, and that these results are then consistent with the human causes having forced the climate system over the past century. The next major issue is, what do we understand about the models? It's clear that the climate models are certainly good enough to reproduce what's happened in the past, in the last 100 years. More and more work, I'll get to this in the next slide a little bit, in terms of going back into the paleoclimate settings and looking at how well the models can reproduce paleoclimate setting is an issue left for future research. And then what do we know about predictions? We know that they require quantifying uncertainty in both the inputs and the different components of the models. And so in order to make sufficient predictions for the future, we want to make sure that the distributions for the inputs are well quantified. We also want to know what the overall uncertainties are in the different components in order to make reasonable predictions. So what are the open questions about the climate model predictions? First of all, the observations have their uncertainties. We want to be able to use that information to understand the climate system variability, and whether or not the changes of the 20th century, how the observed changes are compare against what the fluctuations are in the natural system, and we have to make inferences from the recent observations as well as the proxy data sets. And of course, this is what was handled yesterday in session CL50. In terms of open questions about the climate models, there's been a lot of work done in the past 10 years, or the past 15 years, trying to assess what the uncertainty is in the climate models. We've learned a lot in this process, but there are still specific issues that need to be addressed. For example, what is the role of the ocean in the climate system is one particular issue that's important to us. And we have to be able to test the climate models and decide how reliable they are. And of course, this will require suitable tests to assess this. And this essentially is what we get into in CL52 tomorrow. And then finally, in terms of the predictions, we have uncertainties in the predictions. We want to be honest about what they are. And this then requires objective and subjective assessments of what the input distributions are, as well as uncertainties about the internal components of the models. And then we have to be clear that there are that any results that we present are going to be conditional upon what the assumptions are that went into it. And then finally, which is sort of why we're here at this press conference, is essentially to how do we deal with communicating the uncertain results to the public, and that's then the next, essentially what Caitlin was referring to earlier. So a little bit of a highlight as to what will be talked about tomorrow. I'm only showing here what we call the solicited talks. Detlef Stammer will be talking about uncertainties in the ocean circulation and how this affects future climate changes. Ron Prinn, who is talking here today, will be talking about the probabilistic forecasts for 21st century climate change. And then Herman Held will be talking about the uncertainties, how the effects of climate uncertainties are changed by looking at the welfare optimal, I'll just give the title, Effects of Climate Uncertainties on Welfare Optimal Investment Streams into Mitigation Technologies. And with that, I'll then pass it on to Ron Prinn, who will discuss his latest results.
Okay, I think we can just very carefully move that over. Okay. So what I'll be talking about tomorrow are the results of a very large exercise that we've gone through at MIT over the past approximately 1 year, and I should say that Chris Forrest has been a part of that effort, and along with 20 or 30 other people. So it is a big team effort. The modeling system that we have is called the Integrated Global System Model, and it is unusual among climate models in that it is coupled and driven by an economics model that projects the economies of the world forward, resolves all of the major agricultural and energy sectors that are involved in producing greenhouse gases and air pollutants, and does the things that economics models normally do. There's trade among nations and so on. But what is unusual is it also projects forward all of the pollutants, and you can see that black box that's hanging down from the human activity model there, and you'll see CO2, methane, and so on. Those are outputs from, if you like, human activity projected into the future. The second component of the model is down here. It's the sort of what most people think of as a climate model, and that is it's got the ocean, the land, the atmosphere, it's got the biology on the land and the biology on the ocean, where they are relevant to the carbon cycle, and on the land to the water cycle and to the reflectivity of the land surface. And then there are interactions back into the economic system due to climate change and air pollution that are included in some of the work that we do. And then a vast array of outputs that help us assess the economic health of the various countries of the world, the physical climate change and its impacts, and the impacts on natural and managed ecosystems being agriculture and forestry. In each of these areas that I mentioned, in the human activity and in the natural earth system, there are very large uncertainties. Right? As Chris Forrest pointed out, there are model uncertainties, and there are also uncertainties in input parameters. So we try to get around that problem of great uncertainty by running a very large number of forecasts. In each single forecast, we're trying to choose equally probable values of inputs, parameters, etc., that sit in the modeling systems. And for example, the three biggest uncertainties in projecting climate at the global scale going into the future are associated with the rapidity of the overturn of the ocean. That's from top to bottom, not the surface currents, but from top to bottom. Secondly, the way you handle clouds and convection and water vapor in the system is the second big uncertainty. And the third is aerosols. These are sulfate aerosols, black carbon, and they are the biggest contributor to uncertainty in the overall energy imbalance that we are experiencing at the present time for planet Earth, which is basically we are getting more energy from the sun than we send back out to space, so we're out of balance and so we're warming up. But they're big uncertainties. So the size of each of the ensembles that we use is 400 members in each of the ensembles, and I'm going to go through just very quickly here and show you in a table a way to think about the odds. In other words, we don't have a perfect forecast. Instead, we present it here in the form of a table that is showing you the odds of making resulting from various decisions. If we have no policy, then we will have about 1,400 or 1,399 parts per million of CO2 equivalent by the year 2100. That's just all of the world purring away. Climate is not a problem. We put out the greenhouse gases and go merrily on our way. And then you'll see various levels of stabilization of the greenhouse gases in the atmosphere, 899, 787, 658, and 552. I want to emphasize that these are carbon dioxide equivalents. They are the effect of carbon dioxide plus the effect of methane and the chlorofluorocarbons and all the other greenhouse gases that have been converted into the equivalent amount of CO2 which would have the same effect on climate. In particular on the radiation balance of the Earth. And to just go through one of the examples here, what are the odds of temperature being greater than change being greater than 4 degrees centigrade, and the period being talked about is the 20-year period of 81 to 2000 is being compared to the 10-year period of 2091 to 2100. You do these long-term averages because climate is a long multi-year average of the weather, if you like. So you see here that with no policy you've got 85% chance of exceeding 4 degrees centigrade. 4 degrees centigrade is a very, very dangerous amount of warming. That's 8 degrees centigrade of polar warming, for example. But if I go down the list further and I look at stabilizing at, say, right down here at 552 parts per million of CO2 equivalent, we're going down to less than 0.25%. I think it's supposed to be 0.025%. It's less than 1 chance in 400. In other words, there was no, no, that is correct, it's 0.25%. Not one of the 400 forecasts was over 4 degrees centigrade. So the value of the policy then is very clear. Even though you've got great uncertainty, you can see that you've lowered the odds of a dangerous outcome very significantly. And so that's one way of presenting the results that I would ask you, is that easy to understand? Can you see that what you're really doing with policy is lowering the odds of the dangerous outcomes? You're not totally ruling these things out. They may still have some very, very low probability, but you've just lowered the odds very, very significantly. Most people would feel very comfortable with 0.25% odds versus 85% odds, right? So it is a way. Another way to present the results is to put it on wheels of fortune. We call this the greenhouse gamble. And these are wheels that you can decide to spin. The one on the left-hand side is the no policy wheel. It's taking the odds of various amounts of warming, and you can see that there's 1 chance in 4 of greater than 6 degrees centigrade global warming in that no policy case. All right, and that means 1 chance in 4 of greater than 12 degrees centigrade polar warming. That definitely would lead to the irreversible loss of both the Greenland and Antarctic ice sheets, with all of the huge amount of sea level rise accompanying that event. The one on the right-hand side is the one for stabilizing at 658 parts per million of equivalent of CO2. That's underneath that is 550 parts per million of real CO2, and then the rest of, is the additional effects of methane and other greenhouse gases. And at the moment we're spinning the wheel on the left-hand side. And our message, and I think it's the message from almost all climate scientists, is let's move to the wheel on the right-hand side, or to one with even more favorable odds, but let's get off the wheel on the left-hand side where we are now. Thank you.
Just setting up the... Oops. Back to the beginning. Right, well, I'll be sort of continuing the theme of risks of future climate change, but I'll be trying to tell to you something about some new work which is trying to make sense of new information that the climate modelers are now making available to people who are working with looking at possible impacts of climate change, and by those people we also obviously include decision makers. So what are the new approaches then to assessing climate change impacts that we'll be exploring in our session? Well, I'll first just mention to you what the conventional approaches are for assessing impacts using climate change scenarios, and then I shall turn to looking at some risk-based approaches that use probabilistic information, the sorts of information that Ron just gave you some samples of. Traditionally and conventionally, impact analysts, whether they're looking at agricultural impacts or impacts on forests or hydrology, often work with impact models, and they tend to require climate information in order to estimate how the impacts of climate change in the future might affect their system. And typically they would select from a range of different climate model estimates scenarios, several scenarios typically. Depending on what's available, they'll take a sample of those,
and then they can summarise that information as an average of the climate change estimated by each of those climate models, or some range, and equally they can then look at the impacts accruing from each of those scenario climates, and similarly look at averages or range of impacts, and then attempt to interpret that information. Now, this approach has been used for many years now, but of course the impacts that you obtain using this method are very much scenario dependent. They depend very much on the scenarios that you select. And this has actually been termed, the scenario group that you actually select, somewhat arbitrary, and often they've been referred to as an ensemble of opportunity by some workers. So it's really a sort of arbitrary approach. Now, an alternative approach which has been made available, made possible, a sort of opportunity for impact analysts, if you like, has come about because of the availability now of many more projections than we had before. And if we turn to looking at impacts in terms of risk, then clearly we need to say, well, risk of what in terms of the impacts? And it's clearly important to determine, well, for our system, is it agricultural yields, is it forest productivity? We need to look at, well, what are the critical changes that we're interested in? Are there some sort of thresholds in those systems that are important to look at? So we need to determine thresholds first of all. Then, with this new large amount of information that's become available in the last few years from multiple climate model projections, this is an example in the corner there showing about 500 different realizations of future climate for the same climate scenario for Northern Europe, changes in temperature and changes in precipitation. Just to indicate that there are many different possible future climates there. Now, if we were to use the conventional approach, we would attempt to run each of those scenarios, because you could treat each of them as a scenario, and there might be hundreds or even thousands of those, through our impact model, and for each of those scenarios one would attempt to estimate, well, has our impact threshold been exceeded? So what are the impacts, and how does that compare with the thresholds we've determined? And from that information then, we might then be able to come up with some estimates of, well, for all of those impacts that we've estimated for all of those scenarios, we can somehow estimate, well, what's the likelihood then of those thresholds being exceeded on the basis of all that information? But of course there is a lot of information there, and many impact analysts feel that it is just simply impossible to run so many simulations of their impact models for hundreds if not thousands of scenarios. So there might be another approach. We could actually attempt to express those different climate futures, those different scenarios themselves probabilistically. And you've seen an example from Ron, and we'll be showing other examples of that from the climate modelers in the session tomorrow. So expressing future climate probabilistically, and then can we actually make use of that information rather than running each scenario in turn? Use the information, the probabilistic information, directly in order to estimate probabilistic impacts. And I'm going to give you a quick example of how we might go about doing this from some recent work as part of one of the EU Ensembles project and some other projects concerning so-called pulsar mires in Northern Europe. Now, pulsar mires are frozen peat hummocks which are found in northern Fennoscandia in Northern Europe. These are sort of permafrost features which are very rich in bird life. And they've actually been red listed by the European Union as habitats that they would like to protect. But already over the last century or so, these have been observed to be declining in Northern Europe, and it's suspected that climate warming is responsible for this. Now, we've already done some work on actually mapping the distribution of these features. The black area at the top of the map there, showing the current present-day distribution of pulsars in Northern Europe. And we've also done a few simulations with models that tell us something about the suitability for the formation and the preservation of these features. The maps you can see at the top there are maps showing for different periods in the future, the 2010 to 2039, that's the near future, the mid-century future, and the end of the century, with two scenarios, that's two climate model scenarios, using the conventional approach to impact analysis, showing the gradual disappearance of those features or suitability for those features. Showing the top model shows that the features will completely disappear by the end of the century. The model at the bottom showing that the disappearance would be more gradual. Can we do better than that though? Because that's just two possible futures being illustrated there. Well, if we are to look at the sensitivity of these pulsars to climate, we can actually estimate that, and the graph at the top shows what happens if you change the temperature along the x-axis or the rainfall along the y-axis, how that affects the percentage change in the pulsar distribution. And as you move towards the top right-hand corner of that graph, you can see that the pulsars would be estimated to gradually disappear as it gets warmer and wetter. What happens then if we actually have information about how the climate is expected to change at different periods in the future, and if that information is expressed probabilistically, then we can attempt to superimpose that on our response surface like this. So that coloured area there is a combination of all the climate predictions from different models and using different evidence of the sort that was described earlier as a sort of probabilistic representation superimposed on our response surface. And as we know, as the climate, this is for a period 1991 to 2020, we can now run this forward in time. We can say for that the probability of total loss of pulsars is 0. If we look at that envelope, because none of that coloured envelope overlaps the area, the white area in the top right hand corner. But if we run this forward in time, as the climate is changing through time, we can, with our probabilistic estimates from models and observational information, we can run it forward in time, and we can look in the bottom right hand corner at the probability of losing pulsar mires. It's increasing through time, and towards the end of the century, the probability of losing the entire area of pulsars is above 80%, according to that graph at the bottom there. So just running that through once again, just to show you, this we feel is quite a powerful way of showing how climate change might be realised in terms of its impacts and the probability of those impacts. So to conclude then, conventional impact studies are based on an analysis with a very limited number of scenarios. And they're arbitrarily selected and not necessarily giving a full information about the uncertainties. Whereas now that we have multi-model climate model projections available, we have an opportunity to look at the risks of impacts in two different ways. We can either use multiple projections, hundreds or thousands, and run them through our models, or alternatively we can use this response surface approach that I've just illustrated. And there are several oral and poster presentations using different examples of this approach that will be presented tomorrow, both in the oral and the poster sessions, and of course you're welcome to attend that.
So, good. Well, thank you. Is this mic working? That was a lot of very concentrated information in a very short time. I'm sure you have lots of questions. Who wants to be the first?
Don't be shy.
Don't be shy.
On the plot shown by Professor Ron Prinn, I was wondering if there was a small typo in there going from...
Quite possible.
Sorry?
Quite possible.
It might be one that's worth clearing up. If you want to go back to the second last, the table. Up one page. I was just wondering, the stabilizing at 899 versus 7, whether either of those two percentages might be...
Which one?
As you go down to greater than 4 degrees,
Oh, yeah,
Yeah.
they've been, yeah, good
They've been
point.
reversed.
whether one or the other of those might need
Yeah,
to be...
they've been reversed.
Okay.
That was the deliberate error that was presented. Make sure you were paying
Yeah, I just want to make sure that...
Very
Thanks.
good.
Anyone else?
I have a question for Caitlin. The public seems to be struggling with the whole concept of climate change anyway.
Yes.
How well do you think they'll cope with the introduction of your bar chart approach?
I think that we have to find a way to convey this uncertainty, and if necessary, we will have to, with the help of as many people as possible who are used to communicating with the public, to provide some illustrations. It may be necessary, for example, in some of the science end of newspapers and so on, to provide a little box on the side that helps people to understand these things. But most people have seen pictures like this, admittedly at school and many years ago, but it's not. I don't think it's that difficult. We can, for example, also print the probabilities on each of the bars as a percentage, and I think that way people will be able to see. Now the difficulty is that there's another step. You present the uncertainty information, and then there's a policy decision to be made. And we've kind of talked about that as if there's a magic threshold. The threshold is easy to find. We identify the threshold, and then we know what to do. But actually, there's another step there, and it's a really, really hard step. And none of us here are experts in that. And I think experts in that are only just emerging. Is that fair to say? There are very, very few people who really have a good handle on how to help make those decisions for the future. And in a way, it's not what scientists are used to being asked to do, and so we're not even training our students to help with that. So if that's something that we need to do, then I think we need to talk as a global community, educators, journalists, scientists, school teachers, about that issue. How do we go about deciding how to identify a threshold, and whether there's a window for that threshold or a fixed number for that threshold? We haven't talked about that enough. And all of the issues we've talked about with representing the uncertainty on the temperature come into play with choosing the threshold as well.
There are a few that are clearly defined, like freezing temperature.
Sure.
Those are the obvious ones.
But many of the thresholds also, though, are compound. They require consideration of several different variables at the same time. So it may be, the example I showed was temperature and precipitation, but there are some very much more complex combinations, and all of those can be very important for some impacts. I mean, one example is the Canadian ice storm of a few years ago now, which was a sort of critical combination of various freezing temperatures, humidity conditions, wind conditions, and all of those had to be right in order for that condition to prevail. And it's a very, very challenging thing for modelers to attempt to actually estimate those types of events, and provide probabilities as well on top of that.
Kurt Giermeier from Nature. I'd like to ask, well, all of you really, do you really think that the concepts that have been proposed are scientifically more honest than the conventional approaches we have been using, or that these concepts make it easier for decision makers to arrive at the correct conclusions as to what needs to be done against climate change? And if so, why do you think that a probabilistic approach will, in the real political world, make it easier for someone to draw a certain conclusion?
I guess my view on this is that this type of information is going to be more useful for the people dealing with the details of the policy making. The public is going to be using this information and in using it to make judgments about the quality of the data, the quality of the forecasts, and these sorts of issues. The actual risk assessment has to be done in order for the policymakers to make decisions. And certainly when you get into multi-million-dollar decisions that are based on climate risk, you want to have reliable information. And this is where putting things in these terms provides a much better picture for those types of decision makers.
But in an ideal world, do you think the decisions would be different from the decisions that are needed, well, in the absence of this conceptual change?
Yeah, say 5 years ago, certainly more so in the United States and in Europe. But in the media, this was presented as a debate with equal weight given to people who said climate was unimportant, it wasn't going to change, and people that perhaps exaggerated on the other end. And certainly that impeded sensible policy. It was presented as a debate and people given equal weight on both sides. This moves the information given to a policymaker to be a more honest representation of where the science stands. The uncertainties are there, but we do know something about their distributions. And above all, we do know about the relative effects of lowering greenhouse gas emissions and lowering the amount of total greenhouse gases in the atmosphere. And by the nature of the climate machine, when you stabilize at lower and lower levels, you do remove the odds, lower the odds of the very large amounts of warming very substantially. It's what some people refer to as the fat tail of the distribution. And what better way to sort of describe that than to give, say, a table of odds or wheels. I've actually used those wheels in testimony to the House Ways and Means Committee in the US Congress, which is probably the most powerful committee in the Congress. And they liked those spinning wheels. They finally saw, okay, there's two wheels there. One if we do nothing and another if we take on a serious target. So it is an effective way to describe these issues to people who are not trained to think in this way. Or everyone on the street knows about odds. They just don't put it in terms of probability distribution function. They see wheels like that and they understand it. They know there's one chance in 52 of pulling the ace of spades out of a pack of cards and so on. They're used to this. You've just got to put it in that language. And so wheels and tables of odds are, I think, an effective way to both impress upon the public the state of the science and why there's risk here and we should be doing something about it despite the uncertainty, but also the people who are actually making the policy in the Congress and parliaments around the world. I think it is all we can do as scientists given these circumstances of not having absolute certainty. The same is true for cholesterol. When you have high levels of cholesterol and your doctor tells you to change your diet substantially, and then you say, well, how much longer will I live? The doctor can only say, well, you'll lower the odds of dying of a heart attack or stroke by 20 or 30 or 40%, whatever the epidemiology that they have and the statistics on that disease. People act on that. They're used to thinking in those terms as well. So I don't think it's an alien way to think about it. And you can tell all four of us sitting at this table feel that this is the effective way to proceed. And if you've got ideas about alternative ways to communicate these scientific results, then that's great as well. The more, the better.
Yeah, just to add to that, I think of course there are the decision process includes people who are experts and are able to make use of this information. Practitioners who are making decisions in hydrology, water managers, for example. They actually have been asking for this sort of information for many years and we haven't been able to provide it until now. And so they do actually have tools available for running their hydrological models or whatever tools they're using that can actually make use of probabilistic information. And as Ron said, this is really a much more honest way of portraying what we know, perhaps than arbitrarily selecting from just a few projections, often on the basis of whether you have something available to you, a projection from a model or something like that. This actually is attempting to bring together all of the climate knowledge there is into a sort of more probabilistic framework that takes into account many different uncertainty sources. And I think this really has to be the way we proceed in providing sort of more technical information, at least for practitioners.
Well, time is almost up. To finish this very interesting press conference, I would like to ask you if you would be able to convey one single message on this subject. What would it be, one by one? Caitlin?
think it's very simple. I think it's that we should all, as ordinary people, want to know what the uncertainties are. We shouldn't be asking anybody to provide us with a single best guess for almost anything. Don't want the single best guess I'll live till I'm 70 from my doctor. Neither do I want the single best guess of the temperature rise being over 7 degrees. I want to see the distribution. And I do that when I go to the doctor, and I'm going to ask other scientists in this area to do the same.
I would echo what she said. but I think to add to that, I guess my view is that we need to be honest about the uncertainties in the climate models themselves, as well as the input distributions that are being fed into them, and then show as much of that information as we can to make it palatable to the public and to the decision makers as they need it. So
I think my plea would be to people who are making projections of future impacts on different sectors of society, not to use a single scenario, as some of them do, but to base their projections on all of the available information, and if that is probabilistically represented, then to do what they can to use that information to come to more balanced conclusions than they might otherwise do.
And I think almost everything that sensible that one could say has been said about uncertainty. I would just add that looking at the risks that sit in this table, for example, I think the impetus for global policy has increased enormously over the past few years as we've got more knowledge. These projections are much more warmer than ones that were around even 5 years ago. And by putting it in this way, looking at the odds and the changing odds, despite the uncertainties, the impetus for serious global policy is stronger now than it ever was. So I hope that our modest efforts among the science community to get these issues across will help impel a global policy. It's needed now, and the sooner we get moving, the less cost it will be to address this issue.
Thank you. Thank you all for coming. The speakers will be available after this meeting if you have any more questions. Thanks very much.